Good evening, students. This is Nirosha, chemistry faculty. Welcome to our Spark Academy. In the previous session, we have learned the chemical kinetics part 1. We have seen few concepts of chemical kinetics. Let us take a quick revision of the part 1 class. Let us see what we have learned. Let us see our first part. We have learned about the what is meant by chemical kinetics, how it affects the rate of reaction. See, we have studied what is meant by chemical kinetics, what are the types of reactions based on rates. They are very fast reactions, slow reactions, reactions taking place at moderate speeds. We have seen the definition of rate of reaction. So what is meant by rate of reaction? Change in the concentration by change in the time. So this is the main concept of chemical kinetics, which define a chemical reaction. Now we have seen few examples how a rate of reaction is taking place in chemical reactions. We have seen average rate of reaction, how it affects in reactants, how it affects in products. If we take in terms of reactants, a negative sign will come in rate of reaction. If we take in terms of products, a positive sign will come in rate of reaction. We have seen few examples, we have solved few questions, and we have seen specific rate of reaction. So, and this specific rate of reaction we will derive a rate law equation, that is the change in the concentration by change in the time is equal to K to the concentration power N. So this is the rate equation. From it we will derive rate law equation. Here K is known as rate constant. Now we have also seen the factors affecting rate constant. These factors affecting rate of reaction, there are few factors which affect rate of reaction. They are physical state of reactants, how this physical state affects rate of reaction. It increases in gaseous state, and next to liquid state, and next to solid state. Next, how concentration affects rate of reaction. It is directly proportional to concentration. Next, how pressure affects rate of reaction. Pressure also directly proportional to rate of reaction. Here radiation intensity of radiation is also directly proportional to rate of reaction. And how temperature affects rate of reaction. Here also temperature increases, the frequency of collision increases, obviously the rate of reaction increases. Next, surface area. If surface area increases, there will be more number of successful collisions, which increases the rate of reaction. That is, surface area is directly proportional to rate of reaction. Next, use of catalyst in a reaction. There are two types of catalyst, positive catalyst and negative catalyst. This positive catalyst shortens the reaction path. This negative catalyst enlarges the reaction path. So this is the graph when we use a catalyst. It decreases the path, and by forwarding the reaction to the products in a quick way. So that is the use of a catalyst in a reaction. So we have also seen what are elementary reactions and what are complex reactions. Elementary reactions are single step reactions. Complex reactions are multiple step reactions, in which each and every step is an elementary step. We have also seen what is molecularity. So molecularity is a theoretical value. It is always a whole number. it never determines the rate of reaction. It never depends upon external factors like temperature and pressure. So this is about molecularity. So these are few examples showing the molecularity of the reaction. Now we have also seen about order of reaction. So what is meant by order of reaction? See, order of reaction is defined as number of reactants which determine rate of reaction. It is the number of reactants whose molar concentration changes during the chemical reaction. Molar concentration will be changed in a chemical reaction. That gives the order of the reaction. It can also be defined as the sum of exponents raised on active masses of reactants. These are the exponents, their sum, that is m plus n sum gives the order of the reaction. So order of the reaction is an experimental value. It may be 0, negative or a fraction. Now this order of the reaction can be determined by the slowest step of a reaction. Yeah, we have seen the zero order reaction. Here zero order reaction is defined as to the concentration whole power 0. The rate of the reaction is directly proportional to the concentration whole to the power of 0. That gives zero order reaction. So this is the equation of rate constant for a zero order reaction. K is equal to x by t. So these are the few examples for zero order reaction. So these are the graphs which we have seen earlier for zero order reactions. We have also seen the half-life time of zero order reactions, that is T half is equal to concentration A naught by 2 times of rate constant. Next we have seen about the first order reaction. So what is meant by first order reaction? Here the rate of reaction is determined by one concentration variable only. Because it is first order, depends on only one variable. So these are the examples, and this is the rate equation for first order reaction. K is equal to 2.303 by T log of concentration of A naught by concentration of A. So this is the graph regarding the first order reaction. Next, T half-life of first order reaction is T half is equal to 0.693 by K. So this shows the relation, the graph between T half and concentration of A naught. Next, you need to remember the units of all the orders of reaction. Here first order reaction units are time inverse. Next we have seen what is meant by second order reaction. So it depends upon two variables or square of its variables. Here units of first order reaction, second order reaction is liter, mole inverse and time inverse. See, this is the rate equation for second order reaction, and T half is equal to 1 by K of concentration of A naught. Then this graph shows the relation of T half and 1 by A naught concentration. This is the graph showing second order reaction with slope K, intercept 1 by A naught, and this is the graph at 1 by A concentration of A at time t. Time is shown on x axis and 1 by concentration of A at time t is shown on y axis. So this is the small preview of our last class. Let us continue our class. Now there is a third order reaction also. So this third order reaction shows the equation in this way. Rate equation minus dx by dt is directly proportional to concentration of A whole to the power of 3 or concentration of A to the power 1 or concentration of B to the power 1 or concentration of C to the power 1. So these are the examples of third order reactions, and this 2 moles of NO plus O2 is giving rise to 2 moles of NO2. So this is third order reaction. Here also 2 moles of NO plus Cl2 is giving rise to 2 moles of NOCl. 2 moles of FeCl3 plus SnCl2 is giving rise to SnCl4 plus 2 moles of FeCl2. So this is for third order reaction. And if it is nth order, so till now we have seen 0 order, first order, second order, third order. So we can write rate equations for all these orders. If it is an nth order, if it is the nth order, so there will be the common rate equation, that is k is equal to 1 by n minus 1 of t of 1 by concentration of A at a time t to the power of n minus 1 minus 1 by concentration of A, initial concentration, to the power of n minus 1. So this shows the rate equation for nth order reaction, and the graph shows in this way. If we need to calculate half-life time for nth order reaction, the half-life time will be T half is equal to, we are limiting it from x towards n, x to nth order, that becomes 2 to the power of x minus 1 minus 1 by x minus 1 k concentration A naught to the power x minus 1. So if the equation needs to calculate for nth order, this is for rate constant, this equation is for half-life period. So next we see pseudo first order reaction. So what is meant by pseudo first order reaction? Pseudo first order reactions are the reactions which are not truly of the first order, but under certain conditions become reactions of the first order. See, understand this? They are not first order, but under some certain conditions they will show properties of first order reactions. Here molecularity is more than 1, but order of the reaction is always 1. So since its order is always 1, it is first order. It is under specific conditions, it is following the property of first order reaction, so it is pseudo first order reaction. So examples of pseudo first order reactions: hydrolysis of ethyl acetate. So this is, what is this? Ethyl acetate. C2H5 is ethyl, CH3CO is formula of acetate. Ethyl acetate, when hydrolyzed, it becomes acetic acid and ethanol. So this forms acid and alcohol. For this equation, rate constant K is given as, we are taking the rate equation similar to that of first order reaction, that is K is equal to 2.303 by T log 10 V at infinite minus volume at infinite. V naught is initial volume, to V at infinite, that is volume at infinite, minus V of t, volume at time t. Here we can see a new term, V at infinite. This is under certain conditions. This is under certain conditions we are using the term V infinite. If we take this hydrolysis reaction to infinite, we are subtracting V infinite minus V naught by V infinite minus volume at time t. So this is the specific condition for pseudo first order reaction. So this gives the order of this equation and rate constant for this equation. And one more example, hydrolysis of sugar. Here we are taking sucrose formula C12H22O11. This on hydrolysis it is giving glucose and fructose. Here rate constant in this case is given as, in this case we calculate rate constant or similarly to this of the first order equation, that is K is equal to 2.303 by T log to the base 10. We are taking here R. What is R? Rotation. R given here is a rotation. For the above example, we are taking specific condition as volume. For this hydrolysis of sugar, we are taking this specific condition as rotation. Here, what is R naught? R naught is initial optical rotation. And here R infinite is rotation at infinite dilution. RT is rotation at time t. Here this rate constant K is equal to 2.303 by t log to the base 10 r naught minus r infinite by rt minus r infinite. This shows the rate equation for hydrolysis of sugar. So these are the specific conditions required for pseudo first order reactions. Now let us see few methods which determine the order of reaction. See, order of the reaction is determined mainly by initial concentration method. See, this is the one of the method to determine order of reaction. Next is integration method. Next is graphical method, when a graph is plotted between 1 by a minus x to the power n minus t and time t, a straight line is formed. So this also one of the method to give order of the reaction. Half-life method, we have seen previously, for every order of reaction we are deriving half-life also. In that way also we can derive the order of reaction. For this half-life method, what we are doing is we are taking the ratio of T half of 1 by T half of 2, that is equal to A2 by A1. These are concentrations to the power of n minus 1. So this gives order of the reaction, where here n is the order of the reaction. Next, Van 't Hoff differential method. So this is the equation to find order of the reaction by using Van 't Hoff differential method. That is, n is equal to, here n is order of reaction, that is log of minus d concentration C1 by dt minus log of minus d concentration of C2 by dt to log of divided by log of concentration C1 minus log of concentration of C2. So these are the methods which determine the order of the reaction. So in the next topic we'll see what is collision theory. So what is meant by collision theory? So for every reaction to happen, to convert a reactant into product, there must be some changes happening in the reactant for converting into a product. So those changes, those collisions, everything are shown in collision theory. Let us see it in detail. A reaction takes place when the reacting molecules undergo collisions with each other. So whenever a reaction takes place, there will be the reacting molecules undergo collisions. It means there will be collisions between the reacting molecules to form into the products. In other words, any chemical reaction is result of effective collisions. So understand this, any chemical reaction is the result of effective collisions. Effective collisions means there will be successful collisions. Because of those successful collisions only the products are formed. Not all types of collisions gives products, only few successful collisions, these are effective collisions, gives products. For effective collisions, colliding molecules must have sufficient kinetic energy, right? For effective collisions, it means for the correct type of collisions, these colliding molecules, the reactant molecules, must have sufficient kinetic energy, because they need movement in them to collide with other molecules. They must have sufficient kinetic energy. Collisions should be properly oriented. It means the orientations must be very proper in them. See, if we are taking the circles as molecules, if they collide in the directions shown in this arrow marks, they form activated complex. Activated complex formation is taking place. It is not a product, it is just an intermediate showing activating complex. This activated complex will result in formation of products. This is the product. Because of effective collisions, there will be formation of products. If the collisions takes place in this way, improper collisions, so there will be no formation of products. These are ineffective collisions as shown in the figure. So the collisions must be in a proper way. If that proper way is showing correct formation, they are called activated complex formation. They result in formation of products. If they are improper, they are ineffective collisions. They do not form any products. So the minimum amount of energy needed to convert a reactant into product is known as threshold energy. So whenever a reactant is converting into a product, the minimum energy required for conversion of this reactants into these products, that energy is known as threshold energy. So this is the minimum amount of energy possessed by the reacting molecules in order to have effective collisions for the formation of product. So this threshold energy is possessed by the reactant molecules. Since they undergo kinetic collisions, they form products. So threshold energy is exhibited only by reactant molecules. Next, see, making a chemical reaction happen faster. So there are number of different things that we can change to make a chemical reaction faster. Yeah. Here we explain the concept of collision theory. We are using the concept of collision theory here. Concept of collision theory and how it can be used to explain effective collisions. Effective collisions and it also affects and can also be used to explain the effects of 5 different factors on the rate of chemical reaction. How the rates of chemical reactions can be affected by using this collision theory. Previously we have seen how the successful collisions takes place. The factors affecting the successful collisions we have seen previously. Here, see, there are percentage of successful collisions more in terms of concentration. In terms of pressure also, there are more percentage of collisions if pressure increases, and in terms of temperature also more number of collisions takes place. In terms of surface area also, the successful collisions percentage increases when surface area increased. So these are the factors which explain the rate of reaction in the form of collisions. See, in this picture we can see correct orientation with sufficient energy. In this way, if the orientation takes place with sufficient energy, products will be formed. If the orientation takes place in this opposite way, there will be no reaction happen. It means that is a wrong orientation. If the orientation happens in this way also, it is a wrong orientation because it is having insufficient energy. So it is also there will be no formation of products in such type of collisions. Only the collisions with a successful orientation and with a good amount of energy will result in the formation of products. If we see, according to this theory, the rate of reaction is given as rate is equal to F into Z, where F is fraction of molecules with potential energy which are greater than threshold energy. Fraction of molecules with potential energy greater than threshold energy. So here F is equal to e to the power of, if we take it in exponential form, it becomes e to the power of minus Ea by RT, where here the Ea is the activation energy, R is the universal gas constant, T is the absolute temperature. Next, activated state or transition state theory or absolute rate theory was given by Henry Eyring. This activated state or transition state theory, we can see it here, when A plus B in presence of C, it is converting into ABC. So this is the intermediate or the transition state. This is ABC is the transition state which is forming the activated complex. When On further reaction, it forms AB separately and C separately, which C gives the required product. Here we can see in the picture the HH and II are showing successful collisions, forming the products of HI and HI. So let us see what is activation energy. In the previous equation we have seen EA. So that EA is known as activation energy. So what do you mean by activation energy? It is the minimum amount of additional external energy needed to change a reactant into a product. See, needed to change a reactant into a product, the minimum amount of energy, additional energy required is known as activation energy, or to make potential energy of the reactants equal to the threshold energy. So the threshold energy is the minimum amount of energy required for converting reactants into the products. Activation energy is the additional external energy. This is the additional external energy needed to change the reactant into a product. So this is denoted by EA, where this activation energy is equal to threshold energy minus potential energy of the reactants. Potential energy of the reactants is the extra energy added to the threshold energy. So if we subtract threshold energy to potential energy, we'll get this activation energy. Here the rate of reaction is inversely proportional to activation energy. It means if activation energy increases, rate of reaction decreases, vice versa. Hence, lower the value of activation energy, faster will be the rate of reaction. See, let us see in this graph. Here we are taking a graph between reaction coordinates and potential energy. This is the initial state, that is before the reaction. The reactants will be here. The reactants will be here. When they undergo collisions with the threshold energy, they reach the transition state. If additional energy is also applied, that is activation energy. If activation energy is also applied, it readily converts into products. Here this is products. So this graph shows how activation energy reflects in the formation of products in a reaction. So from this all above the points, we can derive equation, that is Arrhenius equation. See, this Arrhenius equation is used to evaluate energy of activation and to show the effect of temperature on rate constant. So this equation shows the relation between activation energy and rate constant. Remember this equation, very important equation, that is K is equal to A e to the power of minus EA by RT. If we apply log on both sides, we can get this equation. Log to the base 10, K is equal to log to the base 10 A minus EA by 2.303 by RT. Here A is the Arrhenius or pre-exponential factor. So in order to equate everything, we are using a pre-exponential factor, that is A, and e to the power of minus EA by RT is known as Boltzmann factor. And where EA is 0 or temperature is infinite, EA is 0, or if the temperature is infinite, 0 by something, it is 0, or if the 1 by infinity is also 0, in such case this whole term will become 1. Then this K is equal to A. This rate constant is equal to the pre-exponential factor. This is shown here. And if it is taken between two different temperatures T1 and T2, if we apply this Arrhenius equation between two different temperatures, suppose we are taking the temperatures as T1 and T2. T1 is the initial and T2 is the final temperature. Now the activation energy equation becomes 2.303 R of T1 T2 by T2 minus T1 log to the base 10 K2 by K1. So these equations are very helpful for you in solving the problems based on Arrhenius equation. Many of the problems will come based on these equations. So remember, when different temperatures are given, what is the Arrhenius equation to calculate activation energy. Now let's see graph between log 10 to the base k, log to the base 10 k and 1 by t. So if we take a graph between these two, when a graph is plotted between log 10 k and 1 by t, a straight line with a negative slope is obtained. Here slope is equal to, the slope in such case is equal to minus EA by 2.303 R, that is EA is equal to minus 2.303 R. Here intercept is equal to log 10 log base 10 to A. So these are the intercept if we draw a graph between log 10 k and 1 by t. Suppose if we take the graph for exothermic and endothermic reactions, when we apply activation energy, how the graph changes for exothermic and endothermic reactions. On x-axis we take the progress of the reaction, on y-axis we plot the energy. So if we take here the energy of the reactants, if there are successful collisions to form the products, the activation energy will be as shown in this graph. Energy is liberated for exothermic reactions. So it is showing a peak from the reactants to the products. So this is the graph for exothermic reactions. For endothermic reactions, the average energy of the reaction for the reactants is shown here. Here, since it is endothermic reaction, energy is absorbed. So the energy of the reactants will be very less when compared to that of the energy of the products, because the energy is absorbed. By taking its activation energy, it is converting into products. So this is the graph showing endothermic reaction. So these are the few concepts of chemical kinetics. I request all you to remember the formulas mainly about the first order reactions, second order, zero order reactions and their half-life times, and remember how to calculate the molecularity, order, and how to calculate the activation energy by using these formulas. So these are the important concepts for chemical kinetics. So let us see few questions in this chapter. So one of the question is the rate of particular reaction quadruples when the temperature changes from 293 Kelvin to 313 Kelvin. Calculate its activation energy. So we have already seen the formula to calculate the activation energy, right? So what is exactly given in the question? The rate of a particular reaction quadruples. It means it is increased by 4 times. So quadruple means increased by 4 times. When the temperature changes from, here already it is given in Kelvin, absolute temperatures, so no need to do any changes to it. Then calculate its activation energy. So what is the formula? So let's write what are given in this question. K2 is the rate constant, second rate constant. Here K1 is the first rate constant. Since the rate of reaction quadruples, it means it will be in the ratio of K2 by K1 is in the ratio of 4:1. That is K2 by K1 is 4. And the temperatures T1 is equal to 293 Kelvin and T2 is equal to 313 Kelvin. So what they are asking to calculate? Activation energy. So what is the equation to calculate activation energy? So we have seen, so this is the equation. So this is the equation to calculate activation energy in terms of two rates at two different temperatures. This is the equation to calculate activation energy. Let us see. So what is happening here? Remember the formula, log of K2 divided by K1 is equal to minus EA by 2.303 or 1 by T2 minus 1 by T1. So this is the formula to calculate the activation energy when two different rate constants and when two different temperatures are given. So now apply here. If we apply log of what is K2 by K1, it is 4. That is equal to, we need to calculate activation energy. As per formula it is 2.303 and R is universal gas constant. Here R is written as 8.314 and to the temperatures, what is T2? 313 Kelvin minus 1 by T1 is 293 Kelvin. If you solve this entire equation, you will get the value as 52.86 kilojoule. It is energy, right? Since it is energy, it will become kilojoule per mole. So this is the unit for this. So in this way you can solve this problems. So how? Let's go a simple preview. They are given to calculate activation energy, right? In order to calculate activation energy, we need to take Arrhenius equation. What type of Arrhenius equation? In which two different temperatures are there and two different rate constants are there. So this is the formula for the required answer. So if we apply all the terms here, we can easily calculate the rate, the activation energy. So this is the way we will get finally 52.86 kilojoule per mole. Since EA is the activation energy, we are getting in terms of kilojoule per mole. Let us go into the next question. What is given in the question? The half-life of a zero order reaction having 0.02 molar initial concentration of the reactant is 100 seconds. The rate constant in mole liter inverse second inverse for the reaction is. So understand the question. What is given? The half-life for a zero order reaction is given as 100 seconds. Having concentration as 0.02 molar. So what we need to calculate? The rate constant. So what are the units for rate constant? For zero order reaction, mole liter inverse and second inverse. So to calculate this, we need to take equation related to half-life of zero order reaction, in which a rate constant is there and a concentration is there. So in this, what we will do is, we will take for a zero order reaction, for a zero order reaction, what is the rate equation? T is equal to 1 by K of A naught minus A final concentration by initial concentration. If it is given the half-life of a zero order reaction, half-life of a zero order reaction, that is T half is given as 100 seconds. So T half is given as 100 seconds here. If we take this as T at 50 seconds, half of its time, it becomes 1 by K of A naught by T by 2. That becomes A naught, what K is equal to T half at 50 seconds into 2. That is equal to, what is the initial concentration given? 0.02 molar by T half as 100 seconds into 2. If we calculate this, we will get 1 into 10 to the power of minus 4 mole later inverse and second inverse. So if we simplify this equation, we can calculate the rate constant K as 1 into 10 to the power of minus 4 mole later inverse second inverse. So the option will be A. So remember the equations for the rate constants of zero order, and remember how T half is applicable to it. In that way we can calculate the half-life, the rate constant of this question. Next question. A first order reaction has a rate constant. A first order reaction has a rate constant of 2.303 into 10 power minus 3 second inverse. That is, rate constant means the value of K as 2.303 into 10 to the power of minus 3 second inverse. The time required for 40 grams of the reactant to reduce, so here the weight is given, weight 40 grams to reduce to, this is the initial weight, right? This is the final weight, reduced to 10 grams will be, what is given? Log 10 to the base 2 as 2.303. See, here it is given in terms of weights. But what is the equation for first order? K is equal to 2.303 by time T of log of initial concentration to the final concentration. Since here concentrations are given, this concentration is directly proportional to weight. So in place of this concentration, we will directly take the weight. So what is K value? K value is 2.303 into 10 to the power of minus 3. That is equal to 2.303 by, we need to calculate time itself. So log of A. In place of A, initial weight, that is 40 grams is taken, and in place of A minus X, final weight, that is 10 is taken. If we solve this entirely, we will get this 2.303 and this will be cancelled, and we will get T is equal to 1 by 10 to the power of minus 3 log to the 4. 4 is written as 2 log 2 divided by 10 to the power of minus 3. Finally, on calculation, we will get the time as 602 seconds. So this is the time for this question. This is the answer. 602 seconds are required. Apply this value of 0.301 in place of log 2 and calculate. You can easily get the answer. And next question, in a first order reaction, that is from A to B, if K is the rate constant and initial concentration of the reactant A is 0.5 molar, then its half-life is. So understand the question. In a first order reaction, the reaction is from A to B where K is the rate constant. So for a rate constant, we are taking the rate constant as K. So what is the equation? 2.303 by T log of A by A minus X. So what is given in the question? And initial concentration of the reactant A. What is the initial concentration of the reactant A? A is 0.5 molar. Then its half-life, T half is equal to. So you can calculate it using T half formula. What is T half? What is the half-life period for first order reaction? That is 0.693 by K. So apply it here. So what you need to do is take the formula, let us see the formula here. If K is the rate constant and initial concentration of the reactant A is 0.45 molar, and apply this equation, we will get the T half value. See, if we go to the concept of first order reactions, that is this is the equations regarding rate constant of first order reaction and half-life period of first order reaction. This is they have given the initial concentration. They are asking to calculate the final concentration. Here the initial concentration is here A naught. Here A naught, a concentration of A is A naught by 2 to the power of n. For the final concentration, this is the formula. We have to calculate when we go to the question. Understand the question basically. This is the question. So here the question given is for a reaction for A to B, the half-life here the T half, excuse me, the T half in this question will be of 0.693 by the concentration. What is the initial concentration given there? The initial concentration is A naught, that is concentration of A to rate constant. So this equation shows the half-life period in this question, that is T half shows 0.693 by what is this A? That is 0.5 K. So the answer here is option A. And next, let's see this question. When initial concentration of the reactant is doubled in a reaction, its half-life period is not affected. So what will be the order of the reaction? So understand the question. When the initial concentration of the reactant is doubled, see, initial concentration is doubled in a reaction, its half-life period is not affected. It means the half-life period is not changed. So what will be the order of the reaction? If you understand the concept, the order of the reaction will be of first order, because there is no change in, it is independent of concentration. The first order reaction is independent of concentration. So the order of the reaction is not affected. Next question. For a reaction, activation energy E naught A is equal to 0 and the rate constant at 200 Kelvin is 1.6 into 10 to the power of 6 second inverse. The rate constant at 400 Kelvin will be. So see this, what is given? Activation energy as 0 and temperature given as 200 Kelvin. The rate constant, this is initial temperature. The final temperature T2 is 400 Kelvin. The rate constant will be, what is the value of K? So you need to apply here the Arrhenius equation. Apply Arrhenius equation here. What is Arrhenius equation? K is equal to A e to the power of minus A by RT, right? If we apply log on both sides, this becomes log K, that is equal to minus A by 2.303 RT plus log A. So if we apply log on both sides, this will be the equation. So what is given? If A is 0, e to the power of A is 0 and the temperatures given are T2 and T1 are as 400 and 200 Kelvin. If there are two types of rate constants and there are two types of temperatures in Arrhenius equation, the equation will be log of K2 by K1 is equal to minus A by 2.303 R of minus 1 by T2 minus 1 by T1. So apply in this equation, you will get the answer, required answer. So what is the next question? The activation energy of the reaction can be determined from the slope of which of the following graphs? See, if a question is asked in this way, we need to say the activation energy of a reaction can be determined from the slope of which of the following graphs. So this can be little tricky, but if you understand the concept, that is, this activation energy is related to Arrhenius equation. Arrhenius equation, that is, K is equal to A e to the power of minus EA by RT. So what they are asking, determined from activation energy of a reaction can be determined from the slope. We need to see slope. So what if we need to find a slope? We need to convert it in the form of y is equal to mx plus c. So to this equation, apply logarithm on both sides. If you apply a logarithm on both sides and convert it in the form of this y is equal to mx plus c, you will get a graph in this way. You will get a graph towards the downward slope, where here the slope is equal to minus EA by R, and this is for, since we are applying logarithm, this becomes ln, and this becomes the x term, since it is on x-axis. This ln k will be the y term, and the slope will be the minus EA by R. Since from this slope we can get the activation energy. To define it correctly, so the equation will come here as log of k is equal to minus EA by 2.303 RT plus log A. Log A. Compare it to y is equal to mx plus c. So here the activation energy, we get it from the graph of ln of k versus 1 by t. So convert this log into ln. So this becomes ln of k. This 2.303 by RT will remain as RT, and this 2.303 will be converted into ln of A. So from this equation, if we make it into y equal to mx plus c, we can get the graph of ln k versus 1 by t, which defines the activation energy in its slope. Next question, what is the activation energy for a reaction if its rate doubles when the temperature is raised from 20 degrees centigrade to 35 degrees centigrade? So observe first, it is given in centigrades. First convert these terms into Kelvin. Next, what is given in the question? What is the activation energy for the reaction if its rate doubles? Rates doubles. It means the final rate will be twice that of the initial rate. When the temperature rises from 20 degrees centigrade to 35 degrees centigrade, how can you convert degree centigrade to Kelvin? By adding it with 273. If we add this 20 degrees centigrade with 273, we'll get T1, and this 35 degrees centigrade with 273 will get T2 value, and rates R1 will be, R2 will be twice of R1. Since these rates are directly proportional to rate constants, rate of K2 is twice that of K1. So what will be the ratio now? K2 by K1 is equal to 2, because rates are directly proportional to rate constant. Now apply it in the equation. Apply it in the Arrhenius equation, log of K2 by K1, that is equal to minus EA by 2.303 R minus 1 by T2 minus 1 by T1. So apply it in this way, you will get the value of activation energy EA as 34.7 kilojoule per mole. So the important point here is convert first degree centigrade into Kelvin, and next compare the rates, how they are related and how they are directly, rate is obviously directly proportional to the rate constant K, and if we imply the relation that the ratio of K2 by K1 is 2, we can easily calculate the activation energy. So these are few examples of questions of this chemical kinetics, and let's end this topic of chemical kinetics. Thank you for watching.